So these are the 12.1 notes. This is page 3. So we're going to see notation that looks the same, but is just a little bit different. Okay. But we are going to continue for a minute here on our central limit theorem, the one we looked at in the exploration. Okay. So typically, and we didn't see this in the samples that we used, but for the central limit theorem, our samples have to be large enough. Okay. So that means a minimum of 30. Now, we don't always have samples of size 30, and then we will look at the data just a little bit differently. But when samples are at least size 30, you know that your distribution is going to look normal, okay, your sampling distribution. If we start with a distribution that is already normal, then that sample size can be smaller. Now be careful. We are talking about the size of the sample. We are still taking every possible sample of that size when we consider the distribution. These are not the number of samples. Okay. So the central limit theorem says the distribution of the sample means, so that's if you take a look at that exploration, that is each individual sample, mean was calculated and then dropped into that bottom graph, or the middle. The distribution of the sample mean is approximately normal if the sample size is large enough. And here I was going to write that explanation, and I realize that is up above. So the general rule of thumb is that sample sizes of 30 or larger will have a fairly normal distribution, regardless of the original shape of the population distribution. And hopefully you saw that as you went through the exploration. Okay. Notice this notation. This looks a little different. I've got mu sub x bar. This is the mean of the sample means. And so I am going to highlight here so we can connect it to the parts that it goes with. Here's my mean. That's our mu of our sample means, right? That's our x bar down here. Now the population mean, that's our original mu, is going to be the same as the mean of these sample means. And here's how we find this. We take the sum of all of our x bars. So from I equal 1 to m, that just means when I is 1, that is my first sample. When I is 2, that is my second. I'm going all the way up to m, my last sample. I am adding all those sample means together and dividing by the number of samples we have. So m is the number of sample means. You will never have to do this. It is important to know the notation, though, that mu sub x bar, you are going to need to use that. Okay. So the next one, sigma sub x bar. That's going to be the standard deviation of the sample means. Again, here's my x bar. Those are my sample means. And then sigma, that's what we've been using for standard deviation. So to find the standard deviation of our sample means, we are going to take our population standard deviation and divide it by the square root of the sample size. So sigma is the population standard deviation. And n is the sample size. This is also called our standard error. Okay. X bar, again, that should be somewhat familiar. That is our sample mean. And so we want to, when we want to find a z-score, because we're going to treat these samples kind of like we treat an individual, we're going to take our sample mean, our individual data value, subtract the population mean, the mean of our sample means, and we're going to divide by the standard deviation for a sample of that size. Okay, now, this standard area, the standard deviation, is going to change as the sample size changes. So the larger sample size means we're dividing by a larger number, means our standard deviation is going to be smaller. Example 2. I want mu sub x bar, the mean of the sample means. We know that is the same as our population mean, which here they tell us is 64. Pretty straightforward. Our standard deviation is going to be our population standard deviation divided by the sample size. Our population standard deviation is 18. Our sample size is 36. So the square root of 36 is 6. We get a standard deviation of 3. Notice with our original population, the standard deviation is 18, right here. With a sample of size 36, because we are pulling from our population, that standard deviation is now 3.